Hello and welcome to our next set of algebra notes. We are on Unit 2, Outcome 8. We're going to continue on working with these larger polynomials and solving them. Last time we kind of noticed that we really could depend on the graphing calculator to get our initial zero that we were going to divide out with synthetic division, and then we tend to use the quadratic formula to solve the rest. We're going to basically use the same method here, but I do want to introduce the technique that people would use if they didn't have a graphing calculator. So if you're going to solve a larger polynomial and you don't have a graphing calculator, you do actually use a form of guess and check, not the guess and check your book recommends, where they just say randomly pick a number, because there are infinitely many numbers, and guessing a random number is a terrible method when there's infinitely many choices. So I really don't know why the book even recommends that. I don't know any other teachers that would. So instead, we actually use what's called the rational zero theorem. And again, this is something people use before we have calculators. Nowadays, we don't use this so much, so I'm not really going to use it for much else. I will cover it here partially because you might take a class with a future teacher who doesn't let you use a calculator and they would expect you to know this rational zero theorem. Also, I will throw one of these on the test. It'd be a good multiple choice question, so you definitely want to be ready for that on the test because I do want to make sure you pay attention, you know how to use the rational zero theorem. After this test, we won't need it anymore because I'll just let you use the calculator for anything like this. So, okay, if you have a polynomial like this, there's a rule, it's called the rational zero theorem. It says that any rational zero, so meaning zeros that are like fractions or whole numbers, not any zeros with like roots or imaginary numbers. This doesn't work for roots or imaginary numbers. It only works for the nice roots, the whole numbers and the fractions. Any zero of it, so if you have a p over q that's a zero of the polynomial, so some kind of fraction. Q on the bottom could be 1, so this could be a whole number if p is a number and q is 1. But so any whole number or fraction that's a 0, then the top, the p, has to be a factor of the constant term, which is the last term at the end of the polynomial, and the q has to be a factor of the leading coefficient, the front term. And that's the important thing, is that when you make a fraction or whole number 0, so if p over q, the fraction p over q is a 0, then p is a factor of the constant, so the top is a factor of the last number, and q is a factor of the leading coefficient. So q is a factor of the first number. So in this case right here, we'd have that p would be a factor of 6, negative 6, the last number, and q would be a factor of 4, positive 4, the first number. So the top number p always comes from the last number, the bottom number q always comes as the first number. Now factors just means any number that goes into it, right? Divides into it. So of course 6 goes into itself, so 6 would be a factor of 6. 2 is a factor of 6, 3 is a factor of 6, 1 is a factor of 6. So all those numbers would be possible numbers you could put on the top. So first we'll list off the possible p's. What could we use for p? Well, p could be anything in this set. It could be 1, like we said. 1 goes into 6. Now, not just 1, but it could be positive or negative 1. Because if I'm trying to get negative 6, you can do 6 times negative 1, and you get negative 6. Or you can do negative 6 times positive 1, and you get negative 6. Basically what you'll see is you always have to include both the positive and the negative number. Because if 1 goes into it, then the other one does as well. So plus 1 and minus 1 both work. Plus and minus 2 work, 2 goes into 6. Plus or minus 3, both those go into 6. Plus or minus 6, and those go into 6. Those are the only numbers that go into 6, right? 4 or 5, none of those numbers divide 6. So those are the only numbers that could be on top. So if you're trying to make a fraction that is a 0 of this polynomial, it has to have one of these numbers on top. Then the q gives us the numbers on the bottom, and it comes from the leading coefficient. Q always comes from the beginning. It always felt backwards to me. I would think the top would come at the beginning and the end of but it's backwards. The top comes from the last number, and the bottom comes from the first number. So you gotta pay attention to that. Okay, so numbers that go into 4, well, that's gonna be plus or minus 1, plus or minus 2, because 2 goes into 4, and plus or minus 4, and that's it, right? Those are the only numbers that divide 4, 1, 2, and 4. Okay, so that gives me the numbers to use. Now I want to make my list. I want to make my list of p over q's, or fractions that could be zeros. Now, these are not guaranteed zeros. We know by the rule we learned last time, or previously, that a degree 3 polynomial like this, the most zeros it could have is 3 of them. And this list is going to be more than 3. And we'll say that, okay, not all zeros. It's just a list of things that might work. Anything that does work, any number that actually is a 0, has to be in this list. You can't have anything else work. So that's why we make this list. It kind of gives us a short sheet of answers that we can use as guesses. Instead of having infinitely many guesses that might work, we'll have a short list of answers that work. So, okay, p's over q's. So again, last numbers over first number. So I'm going to do 1 over 1, which just simplifies to 1, so plus or minus 1. I do 1 over 2, right? 1 over 2 is 1/2. That works. Don't forget the plus or minus. 1 over 4, so 1/4, so plus or minus 1/4. So those are all possible answers. I keep going. I do 2 over 1. That's another one, so plus or minus 2. 2 over 2 is 1, right? 2 divided by 2 is 1, and that's already on there. And you'll see that with repeats sometimes, where when you simplify the fractions, you end up getting the same number over again, and so you just skip that one. 2 over 4, which is 1/2. Well, we already got 1/2, so we'll skip that. 3 over 1, that's a new one, so plus or minus 3. 3 over 2, that's a new one, so plus or minus 3/2. 3 over 4, that's a new one, 3/4. I'm running out of room. I'm going to do another line, plus or minus 3/4. And that's it for 3 over 4. Now we go to 6. 6 over 1 is 6, so plus or minus 6. I give myself enough room. 6 over 2, if you simplify that, 6 over 2 is 3, and we already got that one. 6 over 4, if you simplify that, that becomes 3/2, and we already got that one. So that is everything. We have all those numbers could possibly be zeros. And you see that's what, 2, 4, 6, 8, 10, 12, 14, 16 possible answers, and we can't have them all be answers, right? There's only 3 answers. So if I asked you, what are these solutions? You give me this list, I know you're not paying attention, because there's only 3 possible answers. Remember, the degree tells you the max number of possible answers. This is a list of what the possible answers could be. So this is saying, if you want to make an answer, pick one of the numbers in this list. Everything else isn't going to work. You know, like 5 is not on this list. 5 is not a solution. And by this rule, we know, yeah, because it's not part of this list, 5 is never going to work in this polynomial. It's not going to be a solution. Same thing with 7 or 1/3. Those are all numbers that are not on this list. They can't work. So if you don't have a calculator, you can't just graph it to get the 0. What you would do is you make this list, and then you'd use guess and check with this list. And yes, it is a guess and check with 16 things, and it's not fun. And that's why I just let you use the calculator, because who wants to guess and check with 16 options? But it's much better than, you know, your book saying, here, just randomly guess a number. There's infinitely many numbers. Hopefully you got it right. That's a terrible method. So instead, we just guess, you know, from this list, and it gives us a short list to guess from. So again, if you took a class later on in your courses where a teacher wants you to solve polynomial and you didn't have a calculator, this is the technique you would use. I know some students, that's what they have to do in their college algebra class because their college algebra teacher wants them not to use a calculator. I'm going to just say use a calculator. So when it comes to really finding the 0, go ahead and just use the calculator, get the graph. But this is something you should know how to do. Again, I'd probably ask you one like this on the multiple choice on the exam. It tends to be one of my most missed questions, I think, because I tell everybody you don't have to really worry about it. But I'll just warn you now, I'm going to test you on this. So you need to know how to do it for this exam. It's really not that big a deal, right? You just have to come up with the possible numbers that go into the last number, the numbers that go into the first number, and then just make these fractions out of it. And that's the idea. Once you got that, you've got your list. Okay, now moving on from that, because like I said, I'm not going to really use this really, because we have calculators now that make our life so much easier. I am going to solve some more polynomials. When we solve these in this section, some of these will have, you know, sometimes they'll have rational zeros, whole numbers or fractions. That's what we saw really the previous section. All the polynomials we solved had rational or you know, fraction or whole number zeros. These ones sometimes might have other zeros. So they might have irrational things like square roots. They might have imaginary. They might have i's in their solutions. So that's what we'll see when we solve these ones. And so we'll look for that. First off, to find the rational zeros, remember graph to find the rational zeros. Because any nice rational zero, any whole number or fraction should show up on the graph. So we always graph for the rational zeros. So anything you can see on the graph and you can tell what it is, that's going to be a rational zero. You know, the numbers where you just don't know what it is, it's probably a square root number or something like that. Those are the ones you can't read off the graph. But the ones that show up and you can tell what they are, those are probably the rational. So let's type this polynomial in there. So we have x to the third minus 7x squared plus 13x minus 3, and that's our polynomial. I'm going to go ahead and just graph it, see what it looks like. And again, any x-intercept should be a 0. And so I can see there's 1, 2, 3. Looks like they might all be on here, but when I go to trace, maybe look what they are, you'll notice that they aren't nice whole numbers. So like this one's between 0 and 1. So like 1 is too far to the right, 0 is too far to the left. So something between 0 and 1. The next one is a 1. This one looks like maybe it's 3, so let's try that. So let's try 3. That one is 3. So 3 is a 0. There's a nice whole number, 0. So x equals 3 is a rational 0 because it, it's on the graph. Let's try the last one. The last one is before 4. So if I go to 4, it doesn't work. 4 is too far. So somewhere between 3 and 4. So you can see a couple of them are numbers that are kind of between. They're not nice fractions as far as I can tell. Sometimes you can kind of tell by looking. Maybe you see the first one might be like 1/3. You could try and type in 1 divided by 3 for 1/3. But it's not 0, so it didn't work. You can also look at the table, remember, for some of these values. You can actually find that 3, 0 that we found on the table. That isn't a great way to find the fraction zeros. So if you have the fraction 0, that's not going to help. But for the whole number zeros, the table works pretty good. Okay, we found 1 though, and thankfully that's all we need. When we're doing a cubic like this, you really only need to find 1 on there. So sometimes that's all you'll find. Something like this, and all you'll find is 1 of them. And if that's true, then that usually means the other zeros, either they're not going to show up on the graph, and they're going to be imaginary, or they might be like this one, they might show up in the graph but not be readable, and they'll probably be irrational. They'll probably have some kind of square root in them. So what we do is once we found a 0, we use that synthetic division to divide it out. So I'm going to do synthetic division with 3 out of this polynomial, because I'm going to remove basically that 1, 0, and then I'm going to solve what's left to get the other 0. So I'm going to write down my coefficients. That's how we do synthetic division. So bring down my 1 and -7. Make sure you've got all the x's, right? X cubed, x squared, x. That way you don't need those filler zeros. Plus 13. Because if you do need filler zeros, you want to make sure you put those in. -3. Okay, so that's all my coefficients. I'm going to do like always, I'm going to put my remainder box here because that's hopefully where I get 0. Because we said 3 is a 0, so you should get remainder 0. I'm going to add and I'm going to multiply. I'm going to see what we get. So we always add, we bring down the first number, so it just becomes a 1 down here. 3 times 1 is 3. -7 plus 3 is -4. 3 times -4 is -12. 13 minus 12 is 1. 3 times 1 is 3. -3 plus 3 is 0. And so we got 0, which is a good sign. It means we're doing it right so far. So now we can go ahead and put our x's back in. Remember, you skip the remainder, skip the first number, that's your constant. So 4 is going to get an x, and 1 is going to get an x squared. And again, the degree should always drop by 1. So we went from an x cubed to an x squared. That's what we're doing, x cubed to x squared. So that's good. So this is our equation. So we're going to take that x squared minus 4x plus 1, and we're going to set that equal to 0, and use that to find the other 0. So anytime you have irrational or imaginary zeros, you're going to have to use the quadratic formula because it won't factor. So if I look at this, I think what multiplies for 1 and adds for -4, well, nothing works. The only things that multiply for 1 are 1 and 1, and they do not multiply for -4. So this one won't factor. That means we have to use the formula. You could use the completing the square technique. Again, if that's what you prefer, that's great. I'm just going to stick with the formula because I think it's more straightforward for most people. So we're going to use the formula. Okay, so remember the formula. X equals -b plus or minus square root b squared minus 4ac. Again, that's on your formula sheet, so I didn't make you memorize it. It's a good thing to memorize if you want to put the extra effort because it's good to know, but you don't have to. Okay, so b is going to be, sorry, we're not going to that, we're going to here, using this guy. So b is -4, so a negative b is going to be a negative, so a positive 4, plus or minus square root b squared is going to be -4 squared, so -4 squared minus 4 times a, which is 1, times c, which is also 1, c is 1, over 2a, which again is 1, and that's our equation. Simplify that a little bit, still 4 plus or minus, but the 4 squared becomes 16. Remember, a negative squared always becomes a positive. It's a positive 16. 4 times 1 is 4, times another 1 is still 4. Since those are both positive, this is only negative, it just stays in negative. 2 times 1 is 2. X equals, well, 16 minus 4 is 12, so we get 4 plus or minus root 12 over 2. Remember that with roots, you do need to simplify if you can, and 12 does simplify because you can break 12 into 4 times 3. So square root of 12 becomes square root of 4 times square root of 3. And then we square root the 4 to get 2, and we leave the 3. So this actually becomes 2 root 3. So we get x equals 4 plus or minus 2 root 3 over 2. Last thing, now that I've got the 2 outside of the root, now you can simplify. Remember, you can never simplify a fraction where a root on top and no root on bottom. Those don't simplify. You have to have both roots or both non-roots. And by getting this 2 out of the root, now we have 2 non-roots. So now they can simplify. When you divide here, make sure you divide everything by 2. So divide the 4 part by 2 and this 2 part by 2. The plus or minus is what separates the 2 parts. So that's why this is all one part, 2, 3. So they only divide and cancel the 2 here. So we end up with a 4 divided by 2 is 2. These 2's cancel, and we just end up with root 3. So plus or minus root 3. And those are the other 2 solutions. So we got one of the solutions. X equals 3 was the first solution, right? That's the only rational 0, because it's a nice whole number. You can think of it as a fraction if you want to do it as 3 over 1. These ones are what we call irrational. These are irrational zeros because they have a root in them. And again, that's why when you looked at the graph, you got weird decimals for those 2 numbers. They're not going to be nice numbers. They end up with decimals that are not helpful to like try and read off the graph. But you can solve and find them, and that's what the answers would be. If you type 2 plus root 3 in your calculator, and it would be at 0 for that number. That would be at 0, or 2 minus root 3. So those are the 3 zeros. So we got one rational one that we could get from the graph, and the other ones we get by using the quadratic formula. On the quadratic we got after we divide out the first one. And so this is why you can't just graph and get all the answers, because we could see all the answers, but we couldn't tell what 2 of them were. And so this is why last section I warned you not to just graph and get all the answers every single time. Because a problem like this one, you're going to need to do this method to get the answers. You have to figure out the 1 from the graph, divide it out, and then use the quadratic that's left in the formula to get the other 2 answers. And you'll see that's the way we're going to do all the problems of this section, because they'll all work out that way. Again, this one's your rational 0, this one's the other zeros. I think some of the homework questions, like my lab, will actually ask what are the rational zeros and then what are the other zeros, or the other or irrational. We'll use either word. And I'll do the same thing on the test. I'll ask for the rational zeros and the other zeros. There might be irrational numbers, there might be imaginary numbers, that kind of thing. So, all right, let's do some more examples of that, but that's the idea. It's a lot like what we did last section. It's just that now we're having all kinds of zeros. And this little chart here is just a kind of way to show you all the different kinds of zeros you can get. So they made this really big polynomial. It's factored, so you can see all the different parts. And they showed how sometimes you can have nice whole number zeros or negative numbers like this. You can have fraction zeros, like 1/2. And these are what we call rational zeros. So the rational zero theorem, the possible rational zero theorem we saw last time, again, only gives us zeros that look like that, fractions or whole numbers. Same thing when you graph and you're able to tell what the number is. It could be those kind of numbers. Then we have some zeros that are irrationals. So these are both zeros that are irrational because they have a square root. They're still real because they have no imaginary part. They're still real, but they're not going to be easy to read off the graph. They'll show up on the graph, but they're hard to see on it, like figure out what they are. The last type are imaginary zeros. And imaginary zeros, they don't show up on the graph at all. You can't read them off the graph, and so they're hard to get. Like you can't get them off the graph, so you basically have to use the formula to get them. So these are the different kinds of zeros you can get. You can get rational zeros, or the others, irrational or imaginary. So these would be what we would call other zeros. That's what my math lab calls other, and then you got your rational. So basically, whole numbers are fractions, and you always think of a whole number as a fraction. Put 1 on the bottom, so it's really the fraction zeros, and then everything else. Okay, let's solve another polynomial. So we're going to solve this one's degree 4. So now we know we can have up to 4 zeros. So we're going to try and look and see if we can find them all. Again, first step is to graph it. So first we're going to graph, because that's how we find the rational zeros. So all the nice whole number and fraction zeros we're going to find by graphing. So I'm going to take this, I'm going to type in the calculator and see what we get. So y equals, we got x to the 4th, so x to the 4th, minus 2x squared, minus 16x, and minus 15. Okay, type the whole thing in, hit graph. And again, you can look at the graph, and I usually just look at the graph to find them because it's a nice place to see them, so I can kind of see what they are. Or you can use the second table option. I pressed it too early. Second table, there we go. And you can see the answers here. And so you can see here that the answers are -1 is a 0, and 3 is a 0. So from this one, we get x is equal to -1 and 3. Those would be the rational zeros. So those are real zeros. And those ones you can just get right from the graph, right? We didn't have to do anything besides look at the graph. You can see there's the -1, 0, right there where it crosses, and there's the 3, 0. If you hit trace key, type -1, show you it's a 0. If you type 3, I'll show you it's a 0. But those are the only two we see. So the other ones are either way far out on the graph, and we can maybe try and find them, or they don't even show up. And that could happen if they're imaginary zeros. So let's just assume they're imaginary and see if we can figure them out using our method where we take the zeros we do have, and we'll divide those out first. So I'm going to start off. I'm going to do some division. I'll just go ahead and start with -1. -1. I'm going to divide out this polynomial. I'm going to bring down my 1 for the x to the 4th. And then hopefully you noticed that the next number I bring down is not -2. It's actually 0 for the x cubed that's missing. Remember, you need those filler zeros. If there's any x missing, we got x to the 4th, x squared, we're missing x to the 3rd. That means you need a 0 for that placeholder. Okay, -2 or -2, -16, -15. Now we've got all the coefficients. Now I can do my division, get my remainder, add and multiply. First number you always bring down, so bring down the 1. 1 times -1 is -1. 0 plus -1 is -1. -1 times -1 is +1. -2 plus 1 is -1. -1 times -1 is +1. -16 plus 1 is -15. -15 times -1 is +15. And add those and you get 0. Okay, so it did give us 0. So that's awesome. Now we know that we got the -1 as a 0. That's done. We pulled that out. Now previously, we would have just solved what's left of the formula, but this one, you notice if you put your x's back in, it's actually a cubic. So we can't use the formula on this one because formula is only for quadratics, for squared. But thankfully, we have a second 0. I think we saw this in the last set of notes too. You have more than one 0 on a 4th degree, you have to divide them both out. So that's what we're going to have to do here. So I won't ever give you a 4th degree without at least 2 zeros you can find on the graph, because you'll end up having to divide both of those out before you can use the formula. And I'm not going to go back to the original, just like last time. I'm going to use what I got down here for my coefficients. I'm going to have 1, -1, -1, -15. Those are my coefficients from this polynomial. So basically, I divided out the -1, 0. Now I'm going to divide out the 3, 0. And then what's left, my answer I get down here, that is going to be what's going to give me the other zeros that I'm looking for. And then multiply. Okay. So I bring down the 1, always bring down the first number, 1. 1 times 3 is 3. -1 plus 3 is 2. 3 times 2 is 6. -1 plus 6 is 5. And 5 times 3 is 15. Add those and you get 0. So now we've divided out, shown that 3 is a 0, because we did get 0. So we had the first two answers, right? Those are the first two zeros, the rational zeros. We knew there were zeros as soon as we saw them in the graph, but now we proved it. And then we take this solution, this polynomial down here, put the x's back in. So now we have a quadratic. We have x squared plus 2x plus 5. And we set that equals 0, and we solved to find the other two polynomials. Again, it won't factor nicely. Nothing multiplies for 5 and adds for 2, because 1 times 5 is the only thing that multiplies for 5, and 1 plus 5 is not going to give us 2. So since this won't factor, use the formula. And you'll see this, like I said, this is what we expect in this section. So when you're on the test, you probably expect one of these, because if I gave you a show your work problem that had one where you could just find all 4 on the graph, it's not much work to show. So I'll probably give you one where you can find 1 or 2 solutions from the graph, and then you'll have to use the formula to find the rest. So be ready for that kind of problem on the show your work. Okay, so the formula, remember, x equals -b plus or minus square root b squared minus 4ac all over 2a. Okay, so throwing in there, so we're using this x squared plus 2x plus 5, that's the polynomial you're doing. So the -b is going to be -2. Plus or minus square root b squared, so that's 2 squared, minus 4 times a, which is 1, and c, which is 5, all over 2 times 1. So I got -2 plus or minus 2 squared is 4, 4 times 1 is 4, times 5 is 20, so minus 20, 2 times 1 is 2. Here, 4 times minus 20, you can subtract that, get negative 16. So negative 2 plus or minus root negative 16 all over 2. Remember with the root negative, that's where i's come from. That's an imaginary number. So we're going to take that and split it up to square root of negative 1, which is I, and then square root of 16, which is 4. So this will become x equals negative 2 plus or minus 4i over 2. So I broke that up because we took that in. Square root of the 16 to get 4, so we squared the negative 1 to get the I. Now both parts can be divided by 2. So there's 2 other ones, and both parts can be divided. So we'll divide and we get x equals negative 1 plus or minus 2i. Remember, standard form for these, you always want the real part first, imaginary part second. Thankfully, you're using the formula, they're already in that order, so you're good as long as you follow the steps correctly. So those are the other zeros, the book talks about, right? These would be imaginary zeros. These are not the rational zeros. These are imaginary, which is why they did not show up on the graph. So we were right when we assumed that, oh yeah, we don't see them, so they probably aren't on the graph, and that's true. These ones would never show up on the graph because the graph only graphs the real numbers. It's a real number graph. So that's the idea. If I give you a big polynomial, you should always be able to find enough zeros that are rational ones on the graph, divide those out so that what you're left with is always a quadratic once you're done dividing the rational zeros out. And then you take that quadratic and you throw it in the formula to solve. So you should be comfortable using the formula. You can see how that's going to come into play. This is something we already did this unit. And you should be comfortable doing synthetic division to solve these big polynomials. Again, graphing is just the best way to get the first zero. Sadly, I've seen people on the test where they sit there and they guess and they guess and they guess, trying to figure out what it is. Don't guess, guess, guess. Just look at the graph. The graph is the easiest way to find these. That way you don't have to sit there and guess and check, which is just a terrible method. I'm really sad that your book just keeps telling you that that's the way to do it. It's like, no, guess is a terrible method. You have a $150 calculator. Hopefully it can cost you that much. But if you have an expensive calculator that will graph it for you and show you the x-intercepts. Remember, the x-intercepts are always your rational zeros, and so you can just use those. Okay, that's the first part of this. I do want to talk about a couple of things to know. One thing to know with these big polynomials is there's this theorem about the types of zeros you get when you get irrational or complex zeros. So these theorems state that if you have a polynomial with rational coefficients, that means that the numbers in your polynomial are nice whole numbers. So everything we've done so far, nice whole numbers or maybe even fractions. If your polynomial looks like these, any of these with whole numbers or fractions, I haven't even done fractions, but they could have fractions. Anything like that, if it has rational coefficients and it has a number with a root in it for a zero, so like a plus c root b, kind of like we saw on the first page, we had a root like 2 plus or minus root 3. If it has a positive one there, then it's also going to have, so is also a minus c root b. So basically what this says is it's saying that if you have a 0 with a plus here, you can also have a 0 with a minus here. And they kind of look like the conjugates we saw for imaginary numbers, right? Where you have the same thing, the only difference was the sign in the middle. And that's what you could kind of think of these as. You kind of could think of these as conjugates. And it says here that if one number is a 0, then its conjugate is also a 0. And we saw that, right? With our previous problem, we saw that we had 2 plus root 3 was a 0, and so was 2 minus root 3. So they always come in pairs like this. You're never going to get just one irrational 0. If you have an irrational 0, you're always going to have 2 irrational zeros. They always come in pairs. The same thing is true for complex roots, or roots with i's in them. Now, there's a little bit more of a requirement here. You have to actually have real coefficients. So the numbers in your original polynomial have to be real, so you can't have any i's in the polynomial. I'm not going to give you anything with i's in it, so you don't really have to worry about these conditions. Every polynomial I'll give you is going to have whole numbers or fractions. It's not going to have like roots or i's in it or anything like that. So this one says that if a plus bi is a 0, then so is a minus bi, which again, that is the little conjugate, right? Conjugate is just where you switch the sign. So what these both say is that conjugate zeros come in pairs. That's what this says. So conjugate zeros always come in pairs. If you got one of the pairs, then you have to have the other of the pairs of zeros as well. So you'll see that sometimes they'll have a question where they'll just ask you what are the other zeros. Like here they say that a polynomial has degree 6, and it has rational coefficients, which is a way of saying that they're both going to be real and rational. So these conditions are met. And then it tells us it has the following zeros. So these guys are zeros. Now, because it's degree 6, remember degree 6 can have up to 6 zeros, so it could have more. And this does have more because we know that every imaginary zero like this, every complex zero with -3 plus 4i, has its matching partner, -3 minus 4i. This also has to be a zero. Because of the conjugate pairs rule, you have to have this with a plus and this with a minus. So this has to be a zero. Same thing here with the roots. If it's got a root like this, you take this and you replace it with a minus here, or the minus with the plus, sorry, and you get the other root. So this one also has to have a 2 plus 9 root 5. This one doesn't look like a whole imaginary, but it's got an I here. So you could think of this almost as like 0 minus 7i. And remember that this one is has a conjugate as well. The conjugate of this one would be 0 plus 7i. Or you could just say 7i, right? Because you don't really need the 0 plus. That's why we don't like the 0 minus here. We just put minus 7i. So this is the conjugate of that. This would be conjugate. So these guys are all conjugates. So since we knew this polynomial had these 3 zeros, we know it also has to have these 3 zeros. So these are also zeros. And that's because conjugate pairs. So this is something that's important to know, because if ever have some of the solutions of polynomial, but you're not given all, you can always check to see if it has any i's or any roots, and then that might give you more zeros, because it might give you other zeros that you can get by just making the conjugate. So the conjugate zeros are always also zeros. So that's an important thing to know. Okay, that's the first half of this section, is just solving these polynomials, and you might use this to solve those. The second half dives into going the other direction. Mathematics, we always like to try and do things the other direction when we can. So previously, we were taking these big polynomials, solving them, and by factoring them basically, and then solving them. This part says that basically, if you have the zeros of a polynomial, you can always go back and build the polynomial. And this is using what we call the fundamental theorem of algebra. This is kind of a big deal for algebra people. This says that if you have a polynomial, degree n, where n is at least 1, then there is at least 1 0 if you include all numbers, including the complex numbers. So if you don't include complex numbers, of course, there's always polynomials you can't solve if you don't use i's. So once you're using i's, and you can work with complex numbers, real numbers, all that stuff, then every polynomial has a solution. It's at least a degree 1, so if there's at least an x in there, you can find a 0. And then that actually leads to a following result that tells us that if the polynomial has degree n, then it has n zeros, meaning that the number of the degree tells you how many zeros it has. So the degree equals the number of zeros. So before we were always talking about like the degree tells you the max number of zeros. Well, we were talking about the max number of real zeros. If you include imaginary zeros as well, so not just real numbers but also imaginary numbers, then the degree actually tells you exactly how many zeros it has. And that's what we saw in the previous couple pages when we were solving polynomials. When we solved the degree 4 polynomial, we had 1, 2, 3, 4 solutions if you include the imaginary numbers. And we solved the degree 3 polynomial. So degree 3 polynomial, we had 1, 2, 3 solutions. So this is a rule. The number of the degree tells you the number of solutions for the polynomial. So that's why quadratics always had 2 answers. Now, there was the case where sometimes they had 1 answer and it was repeated. So this is also including like repetitions, right? So if you have something that happens twice, that still counts. So if you allow for repetition and you allow for imaginary numbers, the polynomials always have the same number of zeros as their degree, which means you can always factor them to look like this, where each one of these is x minus a c, where c is one of the zeros, and then there's n many of these. So if this is like a 5th degree polynomial, you'd have 5 of these little parentheses, where it'd be x minus a 0, a number that's one of the zeros. You can multiply it by some number in the front, so you'll see that. We're not really going to worry about that in this class. Some algebra classes worry about that more than we are. We're really just going to worry about trying to make these things, these x minus the numbers. And these guys are your factors, because they're the things you multiply together to get the polynomial. And note that the factors are x minus each of the 0. So the c's here are the zeros. So you can actually go back and you can use this to build polynomials. If you have a polynomial, like here we have a polynomial degree 3, and we know it's zeros. That's the important thing. Here we know it's zeros. Then you can build the polynomial by building its factors, and then the factors are what you multiply back together to get the polynomial. So first note that factors are x minus the 0. So each one of these zeros, we're going to subtract them from x, and that will give us our factors. To make a polynomial, we're going to take the zeros and we're going to make our factors. So we're going to take the 0, 3, and we're going to do x minus 3. I'm going to take the 0, 4i, I'm going to do x minus 4i. 0, negative 4i, I'm going to do x minus negative 4i, so x plus 4i. And these are the factors. So those are the factors. And then to get the polynomial, we just take these things and multiply them back together. And then we can see what the original polynomial looked like in its full form, not its factor form. So we're going to go ahead and multiply these together. Now, just a tip for you. You can multiply these in any order you want. It will work. If you want to make your life easier, if you ever have a polynomial like this where you have the zeros and some of them are imaginary, start by multiplying the imaginary number of parts together first. So always start with those. It just makes the math easier. You'll see as we go, it makes life a little easier because these will always be conjugates. And when you do conjugates, you'll get the i's to go away. So it's better to start with these conjugates and make the i's go away. So I'm going to do that first. I'm going to do here, I'm going to FOIL. Remember when we multiply, we FOIL. I'm going to FOIL. I'm going to do my first, to do x times x, x squared. I do my outside, x times 4i, so I get 4ix. I'm going to do the inside, negative 4i times x, so I get minus 4ix. And then I do my last, so negative 4i times positive 4i. So negative 4 times positive 4 is negative 16. Remember the I squared turns that back into a positive 16, because I squared always switches the sign. So we get a positive 16. So I squared is negative 1, 4 times 4 is 16, and a negative makes that a negative 16. Negative 1 times negative 16 is positive 16. When you do that, the middle two terms cancel. So the middle two terms cancel, you just end up with x squared plus 16. So all the i's went away, and that's why I like to start with the imaginary part first. If you FOIL that out, you get something without any i's in it anymore. Now bring down your x minus 3, because we want to use that, because our next step is to multiply those together to get our polynomial. I'm going to FOIL, but I'm going to kind of do it in a weird order because I want to get everything in the nice order at the end. So I'm going to start off with x times x. That is my first, so I get x cubed. Then I'm going to do my inside second, because this one's going to be negative 3x squared. We know the squared part comes after the cubed part. Then I'll do my outside next, x times 16, because my positive 16x is going to be smaller than my x squared because it's got just a single x. And then my last part, I'm going to do negative 3 times 16, so I get negative, what is that? 30 plus 18, so 48. I think it's 48. Yep. 18 plus 30 is 48. And that's our answer. So instead of taking the polynomial to start with and solving it and getting the zeros, we actually took the zeros, we took the parts that would solve the polynomial, the solutions, and we made factors. We multiplied those factors back together and got the polynomial. So this is the polynomial that would give us those three zeros. If you graph this, it would have a 0 at 3. You wouldn't be able to see the 4i or negative 4i zeros because sadly they're imaginary, so they don't show up on the graph. But you could graph it to see that the 3 is a 0. You could do synthetic division with the 3, or the to check and see if it's a 0. But that's the idea. So this is going backwards. If you're given the zeros and asked for a polynomial, remember you can always create the factors, multiply them back together, and get the polynomial. That's the idea. So that's what they're talking about here. They're saying use the fundamental theorem of algebra. If you have the zeros, and you know all the zeros, they told us there's 3 zeros, they give us all 3 of them, and you go back and get the polynomial. If they ever do this and they skip a 0, they'll skip the negative 4i. Remember the conjugate rule? If 4i is a 0, then negative 4i also has to be a 0. So they might do that to you. If they do, you can always remember the pairs, conjugate pairs, and that way you got all your zeros. Let's try another one of these and kind of see the idea again. Okay, so this one, polynomial degree 6. So this time we're going to have 6 zeros, right? You have 2 is a 0 with multiplicity 3, so there's 3 2's. Negative 1 is a 0, multiplicity 1, so only one of those. And 0 as a 0, multiplicity 2. So notice the multiplicity matters here because some of these zeros we use more than once. We're going to use this 2 3 times. We're going to use the negative 1 1 time. And we're going to use the 0 2 times. So what's that look like? Well, that means that when we make our factors, we're going to do x minus 2. We're not just going to have one of these, we're going to have 3 of them. We're going to have 3 of these because we have 3 2's as zeros, right? So we have x minus 2 3 times. When I do the negative 1 as a 0, I'm going to do x minus a negative 1. Well, I'm going to do plus 1, right? Because that's the opposite. When you do minus a negative, you get a plus. This is only multiplicity 1, so there's only one of these. I don't need a power on that because there's already one there. Last one, 0 as a 0. Well, how does you make 0 0? Well, you just do x minus 0. But if you do x minus 0, no, that's just going to be x, right? X by itself. So you don't really need to put minus 0 because x minus 0 is still x. So x is a 0, so I'm going to put it in the front because I like to have this one in front. And then the multiplicity is 2. And so there's 2 of these. So if 0 is a 0, then that means you have an x without a parentheses. You don't need the parentheses because x minus 0, you already did it. I mean, easy, x. That's the answer. So just get that. Okay. This is what we're going to multiply this time. But I can't really cube this like this. There's a rule for doing it, but we're not going to worry about it. Instead, I'm going to take this, I'm going to write it out. So I'm going to do x minus 2 3 times. So x minus 2, x minus 2, x minus 2. And then times x plus 1. So that's the trick. We're going to write this out, and then we're going to FOIL. And we're going to have to do a lot of FOILing, so we have to FOIL a couple times. We FOIL these together, we FOIL these together. Doesn't really matter which ones you FOIL together. I just know that I'd like to get a lot of FOILing done because I have to end up multiplying these all together eventually. So I'm going to go ahead and start with these two and these two just so I can get started. So when I do my FOIL, remember I do my first. So I do x times x is x squared. I do x times negative 2 is negative 2x. Negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. So that's what I got when I multiplied those two together. I'm going to do these two. X times x is x squared. Outside x times 1 is 1x. Negative 2 times x is negative 2x. And then negative 2 times 1 is negative 2. Don't forget the x squared at the front. Okay, made some progress. But now I need to factor these, FOIL these. But before I multiply these, I'd like to simplify these a little bit, right? You can see that the negative 2x's and the 1 negative x, negative 2x, those combine. So I can make this a little bit simpler. It's like x squared minus 4x plus 4. And here I get x squared minus x minus 2. Now at this point you got to multiply these two. Now the problem with these two is you can't FOIL these. FOIL is only for 2 parts and 2 parts, right? Because this helps you remember like these two times these two. What needs to happen here is you need to make sure that every one of these gets multiplied times every one of these. Now there's a couple different ways to do it. One way is just to draw arrows connecting all of them, right? X squared, x squared, x squared to negative x, x squared to negative 2. And that's how I grew up doing it. That's how I learned what I was doing. Eventually someone showed me that there's kind of a nicer way to organize this. It's called the box method. So the box method, I'm just going to make a big box. And I'm going to make this a 3 by 3 box because each of these polynomials has 3 parts. So I'm going to make a 3 by 3 box. I'm going to put one of these on the top and one of these on the side. I'm going to do x squared minus 4x plus 4 along the top. I'm going to put the x squared minus x minus 2 along the side. And this is just going to help me remember to make all those multiplications happen. I'm going to do x squared times x squared because this first box I'm going to do x squared times x squared, which is x to the 4th. I'm going to do x squared times negative 4x, it's those two, because this one right here is x squared and negative 4x. So I'm going to get negative 4x cubed. So this box is helping me remember to do all the multiplications. Make sure I don't miss any. So by having this box here, if I fill in all the squares, I've done all the multiplications. 4 times x squared is 4x squared. X squared times negative x is negative x cubed. Negative 4x times negative, that's a positive 4. X times x is x squared. 4 times negative x is a negative 4x. X squared times negative 2 is negative 2x squared. Negative 4 times negative 2 is positive 8x. And 4 times negative 2 is negative 8. I'm not done yet because I do have some combining I can do. Notice that the diagonals actually contain some matching terms that can be combined. So those ones can all be combined. So I got the x to the 4th, that's just going to stay the same. Negative x to the 3rd with another negative 4x, that's going to be negative 5x to the 3rd. Got 4 plus 4 is 8, minus 2 is 6, that's 6x squared. 8 minus 4 is 4x, and then minus 8. This is still all being multiplied by this x squared. Don't forget about that x squared. It's think to do all that work and then get it wrong because you forgot the x squared. So this one I'm going to distribute, and every single one of these is going to be multiplied by that x squared. So I get x to the 6th for the first one. That's 5x to the 5th. I'm just adding the powers. 6x to the 4th. That's 4x cubed. That's 8x squared. And that is the answer we're looking for. So that is a 6th degree polynomial, and it should have all those as zeros. In fact, you can graph this and double check, right? You should be able to see that, 2 is a 0, -1 is a 0, and 0 is a 0. If you graph this, those will all show up on the graph. The multiplicity will only show up as whether it bounces or if it's, crosses. So it's a little bit hard. It's not going to tell you exactly what the multiplicity is, but you can at least make sure that you got the right zeros. That'd probably be a pretty easy good way to check if you're ever doing a problem like this with multiplicity. Just graph it and see if it has at least has the right zeros, even if it doesn't have the multiplicity, or if you're not sure about the multiplicity. That's the idea. So if they give you the zeros and there's multiplicity, make sure you include them multiple times. You can't distribute the power. Please don't try and tell me this is x cubed minus 8. This is not, because when you multiply that all out, you get something way bigger. So you just write it out multiple times, and then you do a bunch of foiling. Eventually, you might use box method when stuff gets big. Anytime you have to do like a 3 by 3 or a 3 times 2, or anything bigger than just a 2 by 2, which when we do when we're foiling, we do 2 by 2. But anything bigger, we can use the box method for. That's the idea. I think I have one more example, and we'll call it good. Call it done. So this example, I want to show you this one because this is kind of a little bit of a toughie from the homework, so I want to make sure I showed you one of them at least. Okay, so this is a polynomial. It has degree 3, so we know that we're going to have 3 zeros. Degree 3, and the zeros are -3 and 2 plus root 3. And you go, wait a second, you just said there's 3 zeros. Why did I only give you 2 numbers? Well, this is what I was talking about earlier. Sometimes they'll give you a 0, and they'll expect you to know it has a matching 0. So this one, we know that because 2 plus root 3 is a 0, we know that 2 minus root 3 is also a 0. Remember the rule that if you have a root or imaginary number, you always come with the conjugate pairs. So if 2 plus root 3 is 0, then 2 minus root 3 also has to be a 0. So those both have to be zeros. Okay, so I'm going to do my factors. Remember, factors just subtract the numbers. I'm going to do x minus -3, so x plus 3, right? When you subtract a negative. Do x minus 2 plus root 3. So when I do this, I'm going to do -2, but I'm also subtracting the root 3, so I'm going to do -2 minus root 3. I'm going to write it like that, because it's subtracting all of this, right? Subtracting the 2 and the root 3. And I'm also going to have one where I subtract this one, so I'm going to have x minus 2, and then minus a negative gives me plus root 3. So thankfully, if you mess up the sign, you're probably okay, because you should really just be able to have one with a minus here and one with a plus here. Since you have one with plus, one with minus, that should be true. If you have that, you're okay. The minus in front should be a minus on both of these. So you're subtracting 2 both times, but the inside side, that's what changes. Okay, this one, I would probably start with these ones, with these guys. And this one I'd probably treat like a box method, because you can see you have 3 parts here and 3 parts here. So you could actually treat this like a box method. So I'm going to do a box method here. Even though there's only one x in it, a box method still works. Okay. Box method, 3 parts by 3 parts. I'm going to make a 3 by 3 box. I've got x minus 2 minus root 3. Got x minus 2 minus root 3. And then we're going to multiply it out. So x times x is x squared. Minus 2 times x is minus 2x. Minus root 3 times x, so I get a minus x root 3. I just like to put everything in front of the root. Minus 2x. Minus 2 times minus 2 is plus 4. Minus 2 times a negative root 3, so that's going to be a positive 2 root 3. X times negative root 3, so I get negative x root 3. Negative 2 times negative root 3 is going to be a positive 2 root 3. And negative root 3 times negative root 3, well, negative makes a plus. And if you multiply root 3 times itself, it's like you squared it, right? And if you square root, it cancels, so you just get 3. Okay, some stuff does combine here. So you can see that there's a negative 2x and a negative 2x, those combine. There's a negative root x3 and a negative root x3, so those are going to combine. There's a 3 and a 4 that combine. There's actually these 2 root 3s that combine. So there's a lot of stuff that combines. We're going to have just the x squared stay by itself. We have negative 2x plus negative 2x gives me minus 4x. I'm going to have negative x root 3, and negative x root 3 gives me 2 root 3 x, I'll put it like that. And then I have 4 plus 3 is 7. And I have 2 root 3 times 2 root 3, so I get 2 times 2 is 4. Root 3 times root 3 is 3, right, because you're squaring the root 3 again. So 4 times 3 gives me 12, so this is plus 12. All right, not beautiful, but we can make it a little bit nicer because we can combine these parts. So we can make that x squared. And then this part I'm going to rewrite as minus x times 4 plus 2 root 3 plus 19. And maybe it would be better to keep this separate, but I'll do that for now. We'll see what happens. Okay, so we put those together. That was the important part. Here I just broke this up because I had x squared, x, and then a number. That I might break up again. We'll see what happens. It's not really important which way you have it. Last thing here I'm going to do, I'm going to multiply by x plus 3 because I got to bring that down. So this whole thing gets multiplied by x plus 3 to get my final answer. So here again, I could use, and maybe I shouldn't have brought that up. I'm not going to bring that together. I'm going to skip doing that. I changed my mind. I'm allowed to do that, right? Change my mind. So I'm going to do 2 root 3x. And we'll just treat that as 4 parts. And we'll do multiplication, and we'll do another box method. So let's do a 2 by 4 box. So make a wide box. So 2 rows by 1, 2, 3, 4 columns. So x and 3. And this one's going to be x squared minus 4x minus 2 root 3x and 19. Okay, so now we're going to multiply everything by x. So we get x cubed minus 4x squared minus 2 root 3 x squared plus 19x. I'm going to do all this up by 3, so I get 3x squared minus 12x. And then 3 times 2 gives me 6. So this is going to be minus 6 root 3x. And then 3 times 19 is 30 plus 27, so 57. We've got some stuff we can combine, right? We can combine the x squareds, combine the x's. Might just leave the root 3 stuff alone because it's kind of yucky to try and combine. So I'm going to leave that as x cubed. Here, 3x squared minus 4x squared is minus x squared. And I do have a negative 2 root 3 x squared. Got 19x minus 12x is going to be 7x. So I got 7x. And then a negative 6 root 3 x. And then 57. I really don't know which one my math lab would prefer, whether they prefer something like this, or if they prefer it written this way. I wouldn't give you one this messy on the test, so I'm not going to worry about the test answer, but in my math lab, I'm not sure if they want it just like that, or if they want you to like bring the x squareds together and write it as minus x squared times, 1 minus 2 root 3, and plus x times 7 minus 6 root 3. Let's do that. I don't think there's a real good reason why they would prefer one versus the other. Here, yeah, there's less x squareds, but they're the same thing. Just one's written where you kind of group together the x squareds, and one's where you didn't. So I would think that either should be fine, but if my lab had a preference, they might have a preference for the bottom one. So I'm not sure for sure. Me personally, I would not care. I won't put one like this on the show your work because on the show your work, I think this is a little more work that I'm going to make you do. So if you're doing an exam question, it's going to be more likely to be one of the ones we previously did, where you might have to do some box method, but the numbers should multiply nicely, and you could get a nice polynomial at the end. So this one is really kind of more of a homework question. So you might see something like this on the homework. I just really want to show you what you do when you had like 2 plus root 3 and the 2 minus root 3 as your zeros, and how you can kind of use the box method to take care of that. Okay. So again, this will probably only ever show up in the homework. It should show up on quizzes or exams, so don't worry about that. All right. That's it for this section. We just learned about how to multiply the zeros back together when we turn them into factors and multiply them to get the original polynomial, and that we sometimes solve polynomials, that have other zeros, irrational or imaginary zeros, and then we use the formula to do that after we divide up the rational zeros we get from the graph. And then again, make sure you're ready to use that rational zero theorem to get the list of possible rational zeros and the possible answers. Again, we don't really use that practically anymore because of calculators, but that's something that is kind of a holdover from before calculators. That's it for this section. I'll see you on the next one.